Okay, hello and welcome everyone. So this video is going to be a walkthrough of what could be the third exam in an intermediate microeconomics course. So the coverage is bundling, two-part tariff, oligopoly, including Stackelberg and Cournot, limit pricing, adverse selection, moral hazard. All right, so same with all my solution walkthrough videos. What I'll do is I'll show the exam as I've got it here. So if you want to remind yourself of the exam or haven't yet had a chance to take it, you can go ahead and stop the video, work the exercises here, and then return as I'll go through the walkthrough shortly. So let's see, there is the multiple choice, and then I think there's 4 more longer form questions. So I know this part's a little bit boring, sorry about that, but I don't know, I think this is probably maybe the best way to be able to make this work out. So, all right, 2 more. This one's a longer one, so I'll leave it sit here for a second. There's some additional parts to this question. Well, 1 more part. And then here's question 9 is the last question on the exam. Okay, so I need to go all the way back up to the first one here because there was a problem with how this thing printed. Also, for this first, there's 2 problems with how it printed. I had a LaTeX problem that messed up the demand curve here. So the demand curve we want to use for this one is indeed x is equal to the maximum of 5 minus p and then 0. And then on the exam itself, this question didn't print well, so I took that off the exam. That'll be evident when I go over here in just a second. So, all right, question 1. In Bertrand competition between 2 firms, each firm believes that if it changes its output, the rival will change its output by the same amount. Nope. So firstly, with Bertrand competition, we're thinking about price competition. Secondly, even if we did have quantity competition, which would be Cournot competition, there'd be no reason to think that if you change your output, the rival's going to change their output by the same amount. So this one's false all around. Question 2. Stackelberg leader will necessarily make at least as much profit as it would if it acted as a Cournot oligopolist. That's true, because worst case scenario, they could just set their Cournot quantity, right? They're typically going to set something much larger for a wide class of demand curves. They'll set actually the monopoly output, but they could do no worse than operating as a Cournot firm, right? Suppose 2,000 people are interested in attending Elvisland. If 1 person attends, their demand is given by x is equal to maximum of what I said was 5 minus p and 0, right? There's a constant marginal cost of 2. If they charge a profit maximizing 2-part tariff with 1 price for admission and another for the per ride, how much will it charge per ride and how much for admission? Well, here we have like the identical demanders case. So we want to set price equal to marginal cost. So the correct answer can only be A or B because marginal cost was 2. And then we just have to find out what's going to be consumer surplus at the price of 2, right? So with this demand curve, you'd think of let's see, this is not that demand curve, this demand curve, right? Q is equal to 5 minus P, or P is equal to 5 minus Q. So the vertical intercept is 5. If the vertical intercept is 5, then there's 3 units between the vertical intercept and, $3 between the vertical intercept of 5 and the marginal cost of 2. How many units are actually going to be sold? Well, the number of units actually sold is going to be, if I evaluate this demand at a price of P, it's going to be 5 minus 2 is 3. So it's going to be 3 times 3 is 9 times 1/2 gives me 450. And actually, I guess like if you followed along or had that right answer, maybe you don't need this part here. But since I said this verbally and realized it might be difficult to track because I didn't write this out, let me just kind of explain real quick. So the demand, and sorry, my microphone's really close to where I'm typing, so this could maybe be a little bit louder than I intend. So demand, well, I should say inverse demand is, I'll make this look way better in just a second, 5 minus Q. Inverse demand is 5 minus Q. I can't draw the graph right here, sorry. Wish I could, but I hadn't thought of doing this until just now. So at price of 3, Q is going to be, 5 minus 3, or look at me. Quantity is going to be 3. The vertical intercept of of demand is 5. So the side of our consumer surplus triangle is going to be 5 minus 2. So we compute consumer surplus as 1/2 5 minus 2 times 3, or equals 1/2 9 equals 4.5, 3.5, 4.5. All right. I don't know if I should have done that or not. Now I'm having second thoughts, but hopefully that helps somebody. All right, so the next one. So question number 4, the answer was B, but let me kind of go over this because I got cut off on my solution or on the exam. So moral hazard enters an incentive conflict when there's some hazardous aspect of the job description. Nope, that's kind of the common misunderstanding of what moral hazard is. Doesn't have anything to do with the morality, doesn't have anything to do with the hazard. Employees feel the cost of their effort, but don't necessarily receive the gains of this effort. Yeah, absolutely. So that's the problem, is there's this incentive conflict. It's like the principal agent problem, where you got the principal is trying to hire the agent to do something on their behalf, but the agent feels the full cost of their effort, but not the full returns to their effort. And so that's the problem. Then we get shirking. Employees with some unobserved undesirable trait are more likely to be interested in the job. Nope, that would be adverse selection. Employment contract gives the employee the full returns of their effort. Nope, the full returns of their effort would actually solve the moral hazard problem. Right, so the correct answer here is, I said was B, but it is B. Okay, so let's see. Now the longer form questions. This is a bundling question. Suppose you've got a company that has 2 different types of customers with 50 consumers of each type. Customer sells 2 different products, good 1 and good 2. Consumer may purchase one, both, or each good. We'll assume all fixed costs are already paid. And so we have the willingness to pay. We want to find the optimal prices if they price separately. Okay, so let's see. I forgot when I was typing up my solution, when I was writing up my solution, I forgot that I said 50 of each customer. It's not going to matter for the purpose of pricing, but here I'm multiplying by 1 and 2 instead of, it should have been 50 and 100, but I'll kind of explain that here. So what this table is doing is it's giving me my willingness to pay for each of the types of consumers for each of one of 2 goods, right? And so what I want to do is, if they're pricing separately, I'm choosing, do I want to set the price of good 1 at 45 and have actually type A and type B consumers buying at the price of 45? In which case, so I suppose I had 2 consumers, 2 times 45 was 90. Or would I rather set it at a price of 60 and then just sell it to that type B consumers only, that one consumer? So that'd give me profits of 65. Yeah, if you want to calculate real quick, this would be like 45 times 100, 450, and then this would be 65 times 50. Okay, fine, but this tells us this is enough. Using 2 customers or using 100 is the same as 1 and 50, tells us that the optimal price for good A, or for good 1, is price of 45, because then we'll sell it to both type A and type B consumers. What about the price of good 2? Well, if I set the price of good 2 at 70, I'll only sell to my 50 type A consumers. I said 1, so 1 times 70 is 70. If I set the price of good 2 at 25, I can sell to both types. So I'd actually sell to 100 consumers instead of just 50. Here I said 2 consumers. I'll sell to both, or both types. Either way, we see, well, we're better off actually ignoring type B consumers for the perspective of how we're setting the price for good 2. So the profit maximizing price for good 2 is actually 70, selling only to type A consumers. Profit maximizing price for good 1 is 45, and selling to both types. Right? Okay, so find the optimal prices if we want to sell both goods for a single price, if we want to bundle. Well, to get the bundle price, or to get the amount that each type would pay for the bundle, you just add up how much they're paying for good 1, how much they're paying for good 2. So like mentally, type A consumers are willing to pay 115 for the bundle, but in their mind, they're thinking of, 45 for good 1, 70 for good 2, sounds good. Whereas type B consumers are willing to pay 90 for the bundle, and they're thinking of $65, most of the money going towards good 1, and then a little bit, 25, going towards good 2. Either way, we could either sell the bundle at 90 to both consumers, or 115 to just 1. Or using these numbers here, you could set the bundle price at 90 and sell to 100 consumers, or with the price of 115, sell to just 50. Turns out, if you're bundling, you'd rather sell to both groups. So 180, if we had two groups, beats 115 times one group, right? Or this would be 90 times 100 is bigger than 115 times 50. All right, lastly, suppose there's an increase in demand that raises only the willingness to pay of type A consumers for good 2 from $70 to something higher. How large can that willingness to pay buy before the company definitely no longer wishes to offer a bundle? So what I'm asking here is I want to say, all right, we want to offer the bundle, but if actually this wasn't 70, if it was something really, really big, we wouldn't really necessarily want to offer the bundle because we'd actually just want to price good 2 separately at whatever is that price. And given the way the other willingness to pay are, we might not even want to offer the bundle that only type A consumers would want. We actually might want to sell good 2 to type A at their maximal willingness to pay, and then set the price of good 1 separately so that both consumers would buy. Well, anyway, what I'm asking though is, here we definitely want to use the bundle, and the bundle we're going to try to sell to both groups. At what point would we rather actually not sell the bundle? We just want to set the price of good 2 separately, for instance. Okay, so to calculate this, what I'm going to do is I'm going to say, all right, here's my willingness to pay table. So this was good 1, this is good 2. And if I'm looking at the bundle, well, the bundle for consumer B, that's not going to change. They're always going to be willing to pay 90 for the bundle. The bundle for for consumers of type A is always going to be 45 plus X, where X is how much they're willing to pay for good 2. All right, so if we price separately, what's going to happen? I'll set the price of good 1 at 45, and I'll set the price of good 2 at X, so long as X was, that's a separate question actually, but we need X to be sufficiently bigger than 25. It's got to be bigger. It's got to be bigger than 50. All right. So anyway, let's kind of set that aside. If we're pricing separately, our revenues are going to be 90 plus X basically. And if we sell the bundle, we are going to sell the bundle. We could either sell the bundle that consumer of type B likes, in which case we'll sell to both consumers and our revenues would be 180, or we can set the bundle based on what consumer type A would want, that's 45 plus X. Except if we look closely, we realize, wait a second, if I set the bundle that type A would like, it's going to be 45 plus X, but if I just price separately, my profits are going to be 90 plus X. 90 plus X is going to be bigger than 45 plus X, so we actually are never going to set the bundle that consumer of type A would like. So that brings us back to just comparing when is it better to set the bundle of 2 times 90 and get 180 for my revenue, and when is it better to price separately. So just doing this calculation, turns out if X is bigger than 90, excuse me, then we would no longer want to sell the bundle. All right, so here's a 2-part tariff question. Consider a market with 2 groups of demanders. Most devoted customers have demand represented by Q is equal to 36 minus 3P. Least devoted by Q is equal to 12 minus P. There's no fixed costs. We can treat marginal costs at constant. Marginal cost is 3. Now, here's the 2 kind of scenarios I want us to consider. In the first case, I've stipulated that everybody has to get the same fixed fee, the same membership fee, and the good or service has to be priced at marginal cost. So what this means is the per unit price has to be 3 because marginal cost was 3. And then we have to decide what's that same fixed fee going to be. Is it going to be based off of my smaller group of consumers and then selling that to both groups? Or is it going to be based off of my larger group of consumers and then ignoring my smaller group of demanders? For Part B, it says it's possible to treat the 2 groups of demanders as distinct markets, so we can offer 2 groups their own membership fees and per unit price. This is real easy. This is just like after we've done Part A, this is real easy. This is one where we're just going to say, all right, well, we can separate these 2 markets, so it's as if we can set the optimal tariff for one market and the optimal tariff for the other market. And the optimal tariff is just set price equal to marginal cost and then set the fee, the access fee, equal to the resulting consumer surplus. So that's all we do. There was more complicated versions of two-part tariff, and I've got some of those exercises in other videos. Uh, Namely, one case we might have is where you have to base the membership fee off of the consumer surplus of the smaller group, and then use calculus to write out profits as a function of price. Take the first order condition, solve for price, and then that'll give you the optimal price and the optimal membership. And I've got lots of other videos to do that, though that wasn't what was going on in this question. All right, so firstly, what we got to do is make our graph for both of the demands so we can kind of visualize what's going on. So this is my graph for my most devoted demanders, right? So if demand is Q is equal to 36 minus 3P, inverse demand is going to be 12 minus 1/3 Q. And then my least devoted demanders is going to be price is equal to 12 minus Q, because demand was Q is equal to 12 minus P. Remember, Q in terms of P is demand, P in terms of Q is inverse demand, and they're both the same demand relationship. It's just that when we graph it, typically we put price on the vertical, quantity on the horizontal. And I regret not labeling these here, but the vertical is price, the horizontal is quantity. At a price of 3, we can calculate the resulting consumer surplus. It's going to be 1/2 base times height, so it's going to be 12 minus 3 is 9, and then it's going to be 27. So 1/2 times 9 times 27 is 121.5. Turns out that's actually going to be bigger than the consumer surplus from the smaller group multiplied by potentially selling it to both consumers. So in this case, this area, consumer surplus, area under demand and above the price, is going to be 12 minus 3 is 9 times 12 minus 3 is 9. So 9 times 9 is 81, divided by 2 gives me my 40.5. Okay, so, but if I multiply that by 2, that's 81, which is smaller than 121.5. So the optimal price, well, we got that for free. That was marginal cost of 3. And then the optimal fixed fee, it's going to be 121.25, and we're going to ignore our less devoted demanders. For part 2, did I say this here? Yeah, I said it's better to sell at a price of 3 and a tariff of 121.5 and sell to 1 than to set the price of 3 and tariff of 40.5 and sell to both. All right, so when we can isolate those two demanders, what do? Well, we have identical demanders within each of those markets, so we'll set price equal to marginal cost, and then we'll set the tariff equal to the resulting consumer surplus, which we already found up here. And so my profits are just going to be 121.5 for my most devoted demanders plus 40.5 for my least devoted demanders gives me 162 as my profits. My per unit profits are 0 because we're setting price equal to marginal cost. Nevertheless, actually for these demand curves, this is going to be the ideal kind of profit maximizing situation because I've converted all this consumer surplus in both graphs to producer surplus. It's basically a second degree price discrimination way to get the first degree price discrimination result of fully capturing surplus. All right, consider the following market with two potential firms. Market demand is given by 50 minus Q. All firms must face the same production costs of marginal cost of 2 and fixed cost of 200. Find the single price monopoly price, quantity, and profits. And then find the Cournot oligopoly quantity, price, and profits. And then I'm asking about limit pricing. Okay, so the monopoly case, we're basically going to boil this down to finding the quantity where marginal revenue equals marginal cost. We could write out profit as a function of quantity. That'd be probably the better way to do this. So we'd write out profit equals P times Q minus CQ minus 200, the fixed costs. And then we'd plug in the values we'd have. So it'd be the quantity, 50 minus Q, times Q minus 2Q minus 200. Then we take a derivative and we get this. 50 minus 2Q equals 2. The shortcut is to say, oh, this is a linear demand curve. So I know marginal revenue is going to have the same vertical intercept and twice the slope. Basically for the calculus reason I just stated. So I could skip here and put marginal revenue equals marginal cost. In fact, that's what I did. Then solving, we'll get 48 is equal to 2Q, or Q is equal to 24. The associated price is 26, so my profits are going to be 24 squared minus 200, which is 376. Okay, so what about the Cournot case? So here's my Cournot profits. So this was the market demand, and then this market quantity is the sum of Q1 and Q2, so that's this. So it's going to be 50 minus Q1 minus Q2, and then that whole thing times Q1 minus 2Q1 minus 200. And this is firm 1's profit maximization statement. I could collect like terms, or I could take the derivative first and then collect like terms. Either way, I'm going to get 48 minus 2q, 48 minus 2q1 minus q2 is my first order condition. I'm going to solve for q1. And remember, my advice is whatever is this value right here, I'm going to solve, this is basically, I move q1 to the other side, so it'll be 48 minus q2 is equal to 2q1. And I say whenever this term right here, it's basically comprised of A minus C from the standard demand curve and marginal cost. Whatever is this value, if this is even or if it's nicely divisible by 2, I would consider 25 to be nicely divisible by 2. It's better to just do that division and write my reaction curve like this. Q is equal to 24 minus 1/2 Q, or Q2. That's because then I don't have all these division bars flying around when I'm trying to substitute and then solve my system of reaction curves. I didn't rewrite the problem from the perspective of firm 2 because we had symmetry. We know we have symmetry because we have the same coefficient on Q1 and Q2, and they have the same marginal cost. So that means if I redo the profit expression or profit maximization problem from the perspective of firm 2, I'm going to get the same reaction curve just with swapped subscripts. So I might as well skip right there and just say by symmetry we have the same reaction curve. Now I'm going to substitute this in for Q2, so I've got one equation and one unknown. When you're solving, the mistake you want to not make is when you distribute this minus 1/2 to this minus 1/2, remember that'll be a positive 1/4. And then when you're solving, you'll get a 3/4 Q1. If you get a 5/4 Q1, you know you made a sign error. You probably made this negative. So you want to avoid that. And then just solving, I'm going to get an optimal quantity of 16 for each. The associated price is going to be 18. Profits are going to be 16 squared minus 200. And so that's going to be, 56. Okay, so now I'm going to ask, do we have a situation where limit pricing is going to be effective if I set a price of 12 as my limit price? Remember, the idea with limit pricing is this is not predatory pricing. It's not explicitly illegal. What's going on is you're a monopoly, but you're going to price with a lot more restraint. And so you're going to set a lower price than the monopoly price. And this is going to have, hopefully, two effects. One is any entrant that's going to be prospectively thinking about coming into the market is going to look at the low price and say, oh, wow, this must not be that lucrative of a market if your price is that low when you're a monopoly. And then part two of their kind of belief is going to be, well, if you're pricing low now as a monopoly, you must have really low costs. And so then you must have capacity to price even lower. And this, as a result, kind of discourages, or hypothetically, hopefully, prospectively, discourages firms from trying to enter in the first place. That's what I'm going to ask here is, if we set a price of 12 as a monopoly, will that discourage firms from entering? If we set the price at 12, the market quantity is going to be 38. Suppose an entrant comes in. Now, the best case scenario that the entrant could possibly anticipate is the price stays at 12, right? And so usually when you enter, you're going to increase quantity, price would fall. Let's just say best case scenario from the perspective of the entrant, price stays at 12 and they split the market, which means the entrant's going to make 19, you're going to make 19, and that's a total of 38. So 12 minus 2 times 19 minus 200, oops, it's minus 10, which is negative. So the best case scenario is a negative profit. So yeah, the price of 12 can discourage entry. All right, suppose you run a shop that produces gizmos. Suppose worker has a cost function of 1/2 effort squared minus 4 effort plus 12. Utility is going to be wage minus effort cost, psychological effort cost. Worker has an outside employment option with compensation equivalent to 30 if they don't work for you. Total gizmo production, I made this really easy. Q is equal to E with no random variation. And then you can sell each gizmo for 16,000. Your only labor cost is labor. Suppose you only pay a fixed wage. What effort level will the worker set? Well, the worker's utility is going to be that fixed wage A minus their effort cost. So A minus 1/2 E squared plus 4E minus 16 is this right here. Take a derivative and solve for E. Gives me an effort level of 4. Okay, how much do I have to pay them so they work for us? Well, what's their utility going to be at an effort level of 4? And how does that compare to their outside option of 30? So here I'm going to evaluate utility at an effort level of 4, set that equal to 30 so that I make A large enough that they are indifferent between working for us or taking their outside option, meaning that they're going to get they're going to get a utility level of 30 either way. So if I evaluate this quadratic at 4, this is going to give me A minus 8 plus 16 minus 16, so that's going to be A is equal to 38. is going to be what's necessary to get the worker to agree to work for us. If they do, their utility is going to be 30, which is the same as if they were not to work for us, if they just took their outside option. What about the full employment, full incentive contract? So now what I want to do is I want to set B. I want to give them the full returns to their effort. That was 16. Each additional unit of effort made one more unit of output, for which we were paid 16 in revenues. That was the price. So I'll set B equal to 16. Basically, that's our d pi dE, right? So our pi was 16E minus W. So our revenue minus our cost. Our cost was only labor costs. Okay, so d pi dE was 16. Then their utility is going to be 16E plus their wage minus, 16E is part of their wage. So the incentive portion of their wage plus the fixed portion of their wage minus the cost of effort. So I'll take du dE, and solving here I find E is going to be 20. If I evaluate their utility at 20, set that equal to 30, and find the A necessary to keep them exactly indifferent between working for us and not, I'll find A is going to be minus 154. And so basically they're going to pay us 154, and then we're going to give them 100% commission on all their sales. This seems weird, but basically you're thinking of a situation like a car dealership where the car dealer is open all the time. They might not make a sale, but the person's there. And that's going to be basically they're contributing value, because you can't run the car dealership if there's no one there. Or like a mall kiosk or a stand where you're selling produce or something. Like there's value being contributed by having the worker there on site. And so they're giving us that value. That's the 154. And then we're going to give them the full returns of their effort, the full commissions on their sales. Okay, so does the firm or the worker have a preference between the two contracts? Well, the worker's indifferent. By construction, the worker's going to get 30 whether they work for us, whether they get the fixed wage, or whether they get the full incentive contract. What about for the perspective of the firm? Well, the firm would way rather have the full incentive contract, because then we get profits of 154, whereas our profits with the fixed wage was just 26. The worker is going to accept for what size fee will both parties accept the contract? So suppose you continue with the contract you found in Part C. That was the full incentive contract. Think of A as the fee the worker's paying for the opportunity. So here we're saying, okay, A was 154 to keep them indifferent. That was profit maximizing for us. But what if we use some other A? What are the bounds on what would be acceptable? So we need A to be, the worker is going to accept an A of, less than or equal to 154. So A is how much the worker's paying us, right? And so they're going to pay us no more than 154. If they paid us more than 154, they would rather take their outside option. The firm's going to require at least 128, because otherwise we'd be better off with our fixed contract. Okay, so the range of acceptable prices or fees to make this of A's, the range of acceptable A's is going to be, or fixed wages is going to be from 128 up to 154. All right, last question on the exam. Consider a used car market where the seller's valuations are distributed uniformly from $20,000 to $40,000. Buyers are willing to pay $5,000 more than the seller's valuation. Draw a graph of the seller's value as a probability distribution. This is the uniform distribution. If a car is randomly selected, what's the probability its valuation is lower than $30,000? I selected that really cleverly to help you out later on. Initially, how much will buyers pay for a randomly selected car if they only know the quality distribution but not the value? So we have to find their expected value for a randomly selected car. And then ultimately, what would be the highest seller valuation of any car left in the market? And then we'll find out like what's going to be the equilibrium. Okay, so part A, let's just draw the uniform distribution. So valuations are uniformly distributed between 20,000 and 40,000. That's a range of 20,000. The height, so the PDF for the uniform distribution is going to be 1 over 20,000. So the height of this box, uniform distribution is a box. Normal distribution's a bell. The uniform distribution's a box. We like using it because sometimes it's natural to think of probabilities being like evenly distributed, but then also it's really nice to work with because it's just a rectangle. Okay, so this rectangle has to have an area of 1. That's why this height has to be 1 over 20,000, because for it to be a valid probability distribution, the area under the curve between the bounds that we're defining has to be 1. Okay, so this is the graph. Then if you're looking at this, you're like, wait a second, the middle is 30,000. The expected value of the uniform distribution is going to be lower bound plus upper bound divided by 2. So that's 30. which either you saw that, or you could just look halfway in the middle, and then you know half is smaller than 30,000, half is greater than 30,000, half the values are. All right, so probability that x is less than or equal to 30,000 is 1/2. Part C was if a car is randomly selected, what's the no. Initially, buyers will pay how much for a randomly selected car if they only know the quality distribution. So that's the expected value, 30. But we said buyers are always willing to pay 5,000 more. So it's going to be 35,000 is initially what buyers will offer. But if buyers are only willing to pay 35,000, all the sellers with higher valuations are going to leave the market. So the sellers above 35,000 exit. Now what's going to happen? Well, the expected value has to crash down as well in response. And so then I say, okay, what will be the highest seller valuation of any car left in the market when this is all said and done? So to find this, what I'm going to say is VH is the highest valuation remaining in the market, and then 20 plus VH divided by 2 plus 5 gives us the expected value plus 5. So the expected value is going to be 20,000 plus VH, wherever that stops. Halfway in between is the expected value. That's the seller's valuation of a randomly selected car on that interval. But buyers are willing to pay 5,000 more, so we'll add 5 there. And then just solving real quick, I'll get 10 plus 1/2 VH plus 5, or 1/2 VH is equal to 15, or VH is equal to 30,000, which I picked cleverly right there because hopefully this made this problem a little bit easier to solve. But in any case, if the highest seller's valuation of a car remaining in the market is 30,000 and the lowest valuation is 20,000, the expected value is 25,000, for which buyers are willing to pay 5,000 more, which brings us to 30,000. And so then no further sellers would leave the market. And so the idea is the highest valuation, when this is all said and done, when all the sellers for whom their valuation was above what buyers would have been willing to pay have left, then the highest valuation of any seller remaining in the market ends up being 30,000. When that's true, the expected value is such that buyers believe a randomly selected car is going to be something they're going to be willing to pay, 30,000 for, and that's enough to keep all the remaining sellers in the market, which I think is kind of clever. This is an adverse selection market for lemons problem, and I don't know. I kind of like how hopefully you enjoyed this question because I built it in a way that I thought was hopefully friendly to the student solving the problem. But anyway, I hope you enjoyed this walkthrough, and I'll see you next time.